Okay, so, we are looking at this description logic called ALC, and we want to look at now the application of the Tableau method for deciding on unsatisfiability essentially. And we will see that once you can show unsatisfiability, you can show the other questions that you want to answer, which is subsumption or membership and things like that essentially. So, we had very briefly looked at this algorithm in the last class. So, let us do a quick revision. If you want to show that a knowledge base K entails a statement S, you take the negation of S and add it to the knowledge base, convert it into negative normal form, and then construct an initial graph using the individuals in the knowledge base, and then apply the expansion rules till all the branches are closed. If all the branches are closed, then effectively you have shown that it is unsatisfiable. If you cannot do that, that means the original statement is not true anymore. So, let us look at a small example. As you can see from IIT Madras, where apparently there is a white colored black buck called MIT2 essentially, which some people confuse with being an albino, but it is not really an albino. And the knowledge base that we have says that herbivores are equivalent to, or you can say are, animals who only eat plants essentially. So, herbivore equal to animal and intersection with for all everything that it eats must belong to the class plants essentially. The second statement says that black buck is a herbivore, or if X is a black buck, then X is a herbivore in first order logic, and the third statement says that MIT2 is a black buck essentially. And what we want to show is that everything that MIT2 eats is a plant essentially, it only eats plants essentially, which of course, as we can see it follows, because MIT2 is a herbivore and herbivores eat only plants. So, MIT2 eats only plants, but we want to do this formally using the Tableau method, and the language as you can see is the ALC language that we have been talking about essentially. So, this is a T box. Remember, T box is a terminology box where you only talk about the concepts, you do not talk about individuals. So, there are two concepts here. Herbivores are animals who are plant eaters, animals who are plant eaters are herbivores. So, we have broken the equivalence into two subsumption relationships, and black bucks are herbivores essentially. If you convert this into negative normal form, you can see that the subsumption relation, which is equivalent to the implication relation in first order logic, has been replaced by not something or something essentially. And the negative normal form of the goal, which we said everything that MIT2 eats, after negating the goal, becomes that there exists something which MIT2 eats, which is not a plant essentially, which is of course, the opposite of what we are trying to prove essentially. So, what we are doing is that if we add this negation, then our knowledge base will become unsatisfiable. So, the total knowledge base is the set of all these statements. The first three statements come from the T box, the fourth statement comes from the A box, and the last fifth statement comes from negation of the goal that we are trying to this thing. So, the next step is to now construct a graph using the individuals. There is only one individual in this knowledge base, which is MIT2. So, we create a node for MIT2 and we will create a set of labels for MIT2 that we know. We know that MIT2 is a black buck, which it has been explicitly stated about MIT2, and we also know that MIT2 eats something which is not a plant, which is what came from the negation of what we were trying to show essentially. So, this is the labels that we have for MIT2. And then we start applying the expansion rules one by one essentially. So, we first take the existential rule. So, we have a statement that there exists eats not plant as a label for MIT2. So, this concept that all the things which eat something which is not a plant has been a label for MIT2. So, the existential rule says that create a new node for the role filler. In this case, what is the role between MIT2 and what MIT2 is eating? So, let us call it X. So, we have a MIT2 eats X in the graph, and for this x our knowledge base says that it is not a plant essentially. So, there exists something which mid2 eats which is not a plant. So, that is the application of the rule where we have expanded the statement there eats not plant and created this additional node essentially. Then we take a rule from the T box. Remember, we can always take any rule from the T box, because it simply says this particular rule that we are looking at, it simply says that black bugs are herbivores, which we have converted into negation normal form, and we can apply it to mid2 essentially, which means if mid2 is a black bug, then mid2 is a herbivore essentially. So, we can apply any such statement to the knowledge base, and this statement, remember this notation says that we are adding this to the labels for mid2. Mid2 already had some labels, that mid2 was a black bug, and then mid2 does not eat something which is not a plant, and now we have added these two essentially. And then we have applied the union rule. What does the union rule say? That if it is something union something, you can take any one of them and create a separate branch. So, we are not going to draw the separate branches here, because it is a bit cumbersome to draw. We will take them one by one essentially. So, in this example, we have taken the case that of the two options that were available to us, not black bug and herbivore, we have taken this black bug option and not black bug option, and we have added it here essentially. So, that is the application of the union rule essentially. The moment we do that, we see that there is a contradiction here. We have black bug as a label for mid2 and not black bug as a label for mid2. So, that particular branch is closed. So, let us try the other branch. That means, the other branch was that you are a herbivore essentially. So, remember that there were two options available to us, either not a black bug or herbivore. We have already eliminated this, and so we are trying a herbivore now essentially. So, we have added this now the second branch. Then we use a T box rule, then we pick up a rule from the T box, which says that herbivores are essentially animals who eat plants, which is this statement here, and we add it to the set of labels for mid2, which is shown here, and then this is again a union. So, we have to apply the union rule. Then you can see that if we add this part of this, then it will anyway contradict the fact that mid2 is a herbivore, which is something that we have said somewhere, right. We have added this fact that mid2 is a herbivore, and then we are saying he is not a herbivore. So, obviously, that will lead to a contradiction. So, we are done with that branch. That leaves us a second branch, which is this part, which is what we are adding here. So, one branch we have sort of very cursorily we have dealt with that, and we have added this second branch. So, we added this, and from this now we are selecting this. So, one of the two things that were there in the union, we are selecting that essentially. Now, we apply the union rule. Sorry, conjunction rule here. Where is that? We have this statement that mid2 is an animal who eats plants essentially. We got that from the statement that herbivores are such creatures, and because this thing. So, the conjunction rule simply says that if you have a conjunction like this, you add both the individual elements to the label set, and sort of you are kind of done. So, having done that, we have a statement that everything that mid 2 eats is a plant essentially, which means that if there is any edge going out of mid 2 which is labeled eats, then whatever is at the end of that edge the node you must label that with plant as well essentially. So, that is the universal rule that we apply. So, we add the label plant to x which is what mid 2 is eating, and then we find that the label for what mid 2 is eating is not plant and plant, which is a contradiction. So, even this branch is closed essentially. So, if you now go over this carefully, you will see that all possible branches have been closed, which means that there is no way of creating a model by adding saying that there exists something which mid 2 eats which is not a plant essentially. So, which means that our original statement has been satisfied essentially, which means that there is a statement that you see on the top of this slide which says that the knowledge base entails that mid 2 is only plants essentially. So, let us now look at what are the other kind of things that we may want to reason about. So, we have already seen that unsatisfiability can be done using the Tableau method. Once you know how to do unsatisfiability, the rest can be done in a straightforward fashion. So, you want to ask the question this one, that is C subsumed by D, and then you can see. So, this is a question that you are trying to prove, that the knowledge base entails that C is subsumed by D. If we take the negation of C is subsumed by D, which means if you remember the propositional logic statement, if C then D kind of a thing, which means that the rule that you had, which is the rule that you will apply here, will end up saying that add C to the knowledge base and add not of D to the knowledge base essentially. So, because we are negating it essentially. So, the details are given here, that if you have this, so C subsumes D is same as not C or D, and the negation of that will give you C or not D essentially, which is very similar to the rule we applied in propositional logic Tableau method. So, essentially you add the fact that if this is entailed that C is subsumed by D, then if you add the fact that there is something which is a C which is not a D. So, what something, there is some A in the knowledge base which may there is some individual which is a C, but which is not a D, which means C subsumes, which means C does not subsume D. Remember, C subsumes D means if X is a C, in this case if A is a C, then A must be a D, but here we are adding the fact that A is a C, but A is not a D, and then if you can show that that is unsatisfiable, then we have shown the original query that C is subsumed by D essentially. If you want to show whether two classes are equivalent, then we basically do these two things separately and we are done essentially. If you want to ask the question whether two classes are disjoint, so for example, you have defined men and women somehow, and then you want to show that they are disjoint essentially according to the definitions, which means that they should not have a common element essentially, right. So, if you want to show that this statement is true, which means the knowledge base entails C intersection D, C intersection D is a subset of the empty set, which means it is an empty set. You can show that by saying, by adding that, show that there is some A which is both a C and a D at the same time, and if this now becomes, so K union this statement that there is some A which belongs to both the sets, if that becomes unsatisfiable, that means that you have shown that C and D were disjoint essentially. In a similar fashion, if you want to show that whether a class is inconsistent, which means it basically is an empty set, you can show that there is some A which belongs to the class. If you add that to the knowledge base, then the whole thing will become unsatisfiable. Instance checking, does an individual belong to a class? we can see that by making a statement that the individual does not belong to a class not of C A and adding it to the knowledge base, if you can show that this is unsatisfiable, then we have shown the original thing. So, the whole thing is the same, that you just take the negation of what you are trying to show and add it to the knowledge base and then show that it is unsatisfiable. If you want to do instance retrieval, which are all the individuals which belong to the class C in the knowledge base, then for every individual in the knowledge base you check whether this thing is true and you are done. So, if you can show unsatisfiability, which is what we showed that the Tableau method does, then you can answer all these questions about class subsumption or membership or disjointness and consistency, and all these things can be answered essentially. What is the complexity of this? The complexity is unfortunately not very high, very low. It is falls in non-deterministic exponential time onwards essentially. The more expressive it becomes, the more complex than this, the harder than this it becomes essentially, which is not a very.
For ALC, it is not in NXP time, it's P space and.
Okay, so it is in P space, which is also exponential time, but polynomial space essentially. And as we go to the newer languages, which we will just talk about in a few moments, they go into NX time and so on. And if you go to OWL full, which is basically not a description language, not based on a description language, then that is actually undecidable essentially. So, what are the other things that you could add to description logic essentially? ALC is a very simple language. It does not allow you to talk about numbers. So, the first thing you can say is a kind of thing that we started off with by saying that has at most n role fillers or at least n role fillers essentially. So, this is, if you remember what we had said, what exists to, we had called it child. So, let me just write child here. So, we can add this. So, this is the unqualified number restriction, which means you are saying that you can have at most and at least, and essentially there is this whole family of languages that we have been talking about, and these languages are given by identified by names. So, just as ALC stands for attributive language with complement, we can add more letters to the language, and if you add this unqualified number restriction, you will have to add the letter n to the language. So, there is a language, for example, called Shoin, where this n comes from here essentially, which at one point used to be considered to be something which was used by description logic essentially. Then you can add functional number restriction. So, which means that the relation is a function, which means you can have at most one role filler, which is what is stated here, and that is stated by the letter f essentially. So, you have only one father, you have only one mother, despite some new advances which UK people were saying where you can have 3 parents or something, but that is something new. Then you can have qualified number restrictions, which is what ALC allows. Sorry, it does not, ALC does not allow, but which is what we were trying to get to. So, here we are saying that you have at most n S role fillers who belong to a class C. So, here for example, you have at most 3 children who are doctors, or at least 3 in the next line who are lawyers, for example. So, this is qualified and number restriction. So, we add the label Q to a language. So, there is a language called Shoek, which is a fairly recent language, I think. Then we can talk about role hierarchies and role inclusions. We can say how roles are related to each other. So, some people say that there is an R box. So, we have a T box, we have a box, and we also have an R box, where roles are sort of talked about in respect to each other. So, we can say role inclusion, for example. In this example, here S and R are roles, they are not concepts, they are roles, and then we say that one role is a sub role of another concept. So, obviously, since both roles and concepts are sets, essentially the semantics is that they are subsets of the parent set, so to speak essentially. So, has daughter is a sub role of has child essentially. So, that is an example given here, and then we use the label H, which stands for hierarchy. So, this Schoen and Schoik both allow this, for example. We can talk about role equivalence. So, if you can talk about role inclusion, you can talk about role equivalence, because then both the things apply essentially. We can talk about whether two individuals are the same or different, which is agreement or disagreement. The Teddy is not the same as Theodore, or something like that, or Teddy is Theodore and Teddy is not Beth, and so on. We can define classes using a nominal, which uses the word O, which you can see is appearing both in Schoen and Schoik. Then you can have role composition essentially. So, for example, as you can see, has father composed with has brother gives you a role of has uncle essentially. So, here we are talking about role composition. When we try to define aunt, we try to say that you have a sibling who is a parent essentially. Here we are saying an uncle is somebody. You can define the role uncle by composing the role of father, has father and has brother essentially. And we can talk about transitive roles. So, for example, has ancestor composed with has ancestor will give you another role, which is has ancestor. If you do that, you have to apply the label R, which is for role composition, and there is a language called Sroik. Is that correct?
Yes, sir.
Okay. And then you can talk about inverse roles essentially. So, has child, for example, is the inverse of has parent. You have to use the label I, which is there in all these languages that I have written on the right hand side, as you can see. So, essentially what you can do is you can choose from a family of languages which allow you to express different kinds of things, but you have to keep in mind when you do that your complexity is going to be dependent on how much more you can express. So, this is a general rule that we have been talking about. The more expressive a language, the harder it is to prove things in that language essentially computationally. So, here is a list of some languages that we have seen. ALC, these are the constructs that we saw. Complement, conjunction, disjunction, existential restriction and restriction. So, you can only restrict, there are no numbers involved essentially. There is a language called Sin or Shin, however it is pronounced, which has these transitive roles, inverse roles and so on essentially. So, this I and N unqualified. So, I and N have been added to ALC. So, this is ALC plus I plus N essentially. Then we have this language Schiff and Schick and Schoik and Sroik, and all of them include some of these different languages essentially.
The letter S is for ALC constructs plus transitive rules.
Okay,
Letter S.
so this stands for S,
Yes, sir.
and this will give you I and this will give you N. So, as far as the current state of the art goes, I think this is the most modern, most expressive language for which people have found efficient enough algorithms. Efficient enough meaning they are decidable, and you can answer all these questions in a decidable fashion, which is I think the base for this OWL 2 DL essentially. DL stands for description logic essentially. So, there are simpler languages than DL. So, like we said in the olden times, well, olden meaning relatively speaking, there was OWL full, OWL DL and OWL light. Now, we have OWL 2 full, OWL 2 DL and OWL 2 EL and FL and RL and so on and so forth essentially. So, there is a whole family of languages that you can talk about. Okay, so, these are the references which one of them is this book here, Foundations of Semantic Web. I think the second reference in this set, but interestingly there is a reference here which you should go and look at, which is this one, which is a web page created by Zolin, and all these options that we saw, all these different letters standing for different expressive attributes and so on, you can basically pick and choose. It will tell you what is the language and what is the computational complexity of the language. If it has been proved that This is the complexity. For some languages we do not know how complex they are, which means that they could be undecidable, but it is a very nice site at University of Manchester in the United Kingdom, which incidentally is a stronghold for the semantic web and everything that goes with it, description logics and OWL languages and variations of OWLs. And why are we interested in description logics? Because they give us a kind of a sound foundation on which the language is based, which means that if you are using OWL DL for example, and if it is based on Schroik for example, then you know that you can write programs which will arrive at the inferences that you want to make in a decidable fashion essentially. So, those of you who are really interested in this should really maybe try and get into Manchester, which has quite a few people who work in this area essentially. Okay, so we will stop here, and with this we end our study of description logics. We spend a fair amount of time doing that. To summarize, description logics were languages which are used to describe domains. So, we said that description logics are basically logics of noun phrases. So, we can define concepts, talk about them, talk about relations between concepts, and now we can talk about relations between roles and so on and so forth. And these allow us to give us a foundation for building domains which will be readable on the internet or readable on the web essentially. So, we will move away from this. We will go back to this question of inheritance essentially. What happens where your knowledge base talks about multiple inheritances essentially? Some of them could be contradictory essentially. In which case, what can you believe about an individual which is there in the knowledge base? So, we will take that up in the next class essentially. I think. So, we are done with description logics with this.